Hey gang, how's it going today? Alright, so, fade that out. Oh, couldn't really fade it out, sorry. Hope you guys are doing well. We've got the lab to talk about. This one was relatively quick, I think. I didn't get a lot of questions on it, so hopefully that one is straightforward. And then we've got some new stuff coming up this week. Unfortunately, my wife and the little guy are sick right now, so I'm trying to do double duty, taking care of them. So we're going to have to cut it a little bit short today. I apologize. So we'll probably be able to get through the lab, and then we'll come back for the list stuff on Thursday. Let me just pull this up here, see how we're doing. All right, awesome. Oh, and I'm out of coffee. One of those days, isn't it? It's one pot down already. All right, so this is week 5. Hope it's going well for you and your other courses. I know that means we're a third of the way through the semester already. That's just insane. We're just cruising. All right, got some quizzes and stuff to grade. That's good. I'll get those ones for you guys. Let's see, what else? Come on. Where's our schedule? Let's make sure we're on track. Yep. Also, we did array based sequences, so we'll come back for stacks, queues, and dequeues next. So these ones are actually pretty quick, so we should be fine to tackle that one on Thursday. And then our project is coming up due as well. What's our due date on that one? This is why it's all in Canvas this year. I can never remember any of this stuff. On Thursday. So on Thursday, we'll talk about the solution to the maze solver. And then we'll get into the stacks, queues, and dequeues, or decks, or whatever they want to call them. Those are pretty straightforward, so we should be in pretty good shape. Okay, so I've answered a couple questions. I got out in Discord. I posted what you could add in printing like every step of the way with your maze. Let me pull that one up here. Let's see. I think we've got that over here. Yeah, so throw this down on this screen here. So, excuse me. And again, the start doesn't have to be in the top left, and the end doesn't have to be in the top right. They could be anywhere in this maze. So there used to be a really cool maze generator you could find online that had a nice API, but I think they took it offline. I wasn't able to find it anymore. Let me just make sure that's offline. Yeah, I think they turned it off. So that's okay. It was fun, and we used it before. But so my maze solver just puts a V in. You could do anything you want for your breadcrumbs, and it just kind of is walking you through at how many moves it's counted and what it's currently doing. Right, so you can see each step of the way. So I think my algorithm was up, down, left, right, or something like that. I forget. I'd have to double check. It just keeps on going, and here it hits the dead end. So the next thing that happens, right, it goes right from here. So we don't see the unwinding steps. I didn't bother putting prints in after we unwind. Or start undoing. So the last successful one that had the next move, right, all of these ones undo, we come to here, and now we're trying down. And then we found the solution with 8 moves. Right, from here we hit the end with 8 moves. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 moves from start, we find a solution. And then the next thing that happens, right, now it's trying up. So we got back to here. So we unwind these steps here, and we're back to up. And we try up, up, right? And we eventually work our way around. We find another solution with 12 moves. Well, 12 is not as good as 8, but that's okay. So the next thing that happens is we come back to here. So we've tried right, we've tried up, now we're going to try down. So we go down, 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 right, and we hit the end. So we found another solution with 8 moves. So far 8's been the best. All of those undo. It's tried everything it could. It tried right, it tried up, it tried down, can't go left. So the next place we end up here is where we left off at this location, and we try going down. Try going down, and try going here. Okay? So that's sort of like walking through, seeing it happen visually here is useful. Sometimes running in debug mode can be a little bit tricky. So I put that out there. All right, so for our lab, I've given you guys a little bit of a starter code here. Let me fire up PyCharm. And give me a second. So does that make sense for what we're trying to do then for that maze solver? Again, it should try all of the possible solutions. So once we come back from the recursion, it has to undo. You have to take off that little breadcrumb. Oh, sorry, I'll close that. yeah, so inside the loop, right? So in our case, like with the n queens puzzle, we had a loop that was happening. You don't even need a loop at this point. We're just saying, hey, let's just go right, left, whatever, up, down, left, right, any direction you want. All right, so for n queens, we said we're going to try. If we're not solved, try this. So for every row, try and put a queen on the row. So it's not every row now, because we're not saying do this in every row. We're saying from wherever we are, try up, try down, try right, try left. Or up, down, left, right, up, down. I mean, the order doesn't matter to us. And we're just going to try all of them. And if we can, we're going to do the thing and recurse. When we come back from recursion, we need to undo that thing. Right? We did a similar one with the Sudoku Solver. Let's take a look at that one. For the Sudoku Solver. Right, the idea was, there's our recursive piece here. So we found the next open position in this location. So this one wasn't tracking where it was, because we could just find the next open one. And we tried, in here with this loop, we tried numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? If we can put that number down, we're going to try it and recurse. So again, there's not really a loop there, because we're not trying different numbers. We're just trying up, we're trying down, we're trying right, we're trying left. Okay? Let's see. All right. Oh, look, I had my maze solver showing there. Oops. All right. There we go. I think I got it. So this was the starter code I gave you guys just to take a quick look at how long it takes to append. And hopefully you saw the little stepped graph here, right? So most of them are really, really fast, but every so often you get a spike. Really, really fast, little spike. Really, really fast, little spike. So it doesn't visualize perfectly. Just the axes are a little bit funny on how that works. Run, there we go. But so like it doesn't look like you could lay them down and get constant time operations, but it's just a factor of the axes. All right, sorry, it's still thinking about it here. Sorry. I'm going to answer this real quick. Okay. So there we go. So, ooh, my computer's going a little slow. Those ones are awfully slow there. But you see, we get these big spikes showing up here. So this is just timing. It's not number of operations, but you can see we get these timing spikes. Let me try one more time. It goes a little faster. I wonder, it's doing a lot of things right now with OBS and whatnot. Maybe. Thinking about it. Wow, it's just unhappy today. Okay, that looks a little bit better. It's still not quite as stair-steppy. I think it's just my computer being slow. And that's the problem with doing any of these like compute timings, is it's actually depending on what your computer is doing. Like it's still trying to run that process. That's crazy. Try one more here and see what else we can get. It'll probably be pretty similar. So the idea here, we were just looking at some average timings. So for the lab, we wanted to say, well, how long does it take to remove an item from a given index? So we know, right, every time you remove something, everything has to shift down in place. So we could remove, might remove index 0 and see what that looks like, based on the size. We might remove near the end and see what that looks like. So we can see different timings. There's like one big spike. This looks a little bit more typical, right? Pretty much straight except for those couple of anomalies. So we need to build a list, and then we're going to try removing stuff. Okay? So, great, we'll do the same thing. That's appending an item to the list. So that's compute time to add. Let's do a different one. So we'll add a new function here for, say, define compute time to remove, list to remove from, and index to remove from. Right, why not? You give me a list, so I'm going to start my timer. I'm going to do my operation. So, and removing actually is, it's pop. And you give it a pop the index to remove from. Right, if you think back to your Python lists. So remove can remove a value, but pop will pop an index. Okay, we got that one, and then we're also going to compute how long it takes to insert an item at, say, the beginning of the list. You know, or you could do anywhere, but again, when you insert, everything has to shift down to make room for it. So we'll list to insert into, and the index to insert into. We'll take the list, and we're going to call insert. And insert wants, what is it? Two things. So we can never remember, is it the value first or the other one first? Come on, PyCharm. Help me out here. Some list insert. Okay, so the index first and then the object. Cool. So insert will do the index first. And really the value doesn't matter, so we'll just duplicate that. So it's the index, then value to add. The value doesn't matter for our purposes here. Right? So we have our list then. So we can use this values list for the ones that we want. Just, or the sum list here, if we want to keep that, because we know we added a bunch of things to it. But once we remove or insert, oh, that's right. Computer time, compute time to insert at index. Move from index. There. Okay, so we're just trying to see how long this is going to take. So we can add a couple plots. So we'll hold off on this one for now, right? So that's 10 million. Yeah, we'll wait on that one, and we'll do. So let's see. I want to keep all those ones there. We'll comment it all. We'll do our own. So again, we'll have a timings list here, and then we'll have the values is going to be a list of range of 10 million. Right, and then again, we just want to do this sort of operation. So for n in values, we'll take our timings. We're going to append whatever we get back from our compute time to remove from index. And then we'll remove. Every time we just want to remove index 0. We're going to take the first thing out and everything will slide down. Take the first thing out and everything will slide down. We'll take the first thing out and everything will slide down. So it should start very slow, and then it should progressively get faster as we have less things to shift. Is kind of the idea here. Okay, so we're going to plot the values and the timings. That's going to be backwards, isn't it? It's because, oh, was it even to do 1 million? It took a while? Okay. Yeah, it's going to depend a little bit on your computer too. So the timing then, so the size of n is going to be different, right? So we want to, let's have, let's make a list, right? So timings and size of list. Here we go. Oh no, so size of list is another list, and then we'll take that. Oh, this one is, yep. So size of list dot append, the length of, what is it, our values. Oh, we need to tell it the list too. So values and index, right? The list to remove from and the index to remove from. So if we give it values, we should be able to figure out how long it takes. Okay, and then we're gonna, so that will be our y-axis, or our x-axis, right? And our y will be the timing. So the size of the list is big, going to smaller, Okay, let's give this a shot. So we're going to add, start with 10 million things. We're going to take one item out, the first item out, and everything will have to shift. Everything will have to shift. Everything will have to shift. So it's going to take a while with all the shifting. So maybe 10 million was too aggressive. We'll try with just 1 million. See what we get. Because remember, every operation then is doing 1 million shifts, and then 999,999 shifts, and then less shifts, and less shifts. So it's going to do a lot of shifts as we go. It's still thinking about it. Oh man. All right. Let's try a little bit less then. Try 100,000. I just want to get something going real quick. And we could let it run a little bit longer if we were curious, but okay, just going to 100,000. So some of them are faster, right? Some are slower. So not quite a perfect step here. So let's see. Let's print out the size of is it CIS, right? So import CIS. CIS dot size of. And let's see what our size of values is as we go. So I'm just going to print that, and we'll see. I guess we could add another plot for that too. That might be interesting. Oops, isn't it sys.size of? Get size of. Okay, that's boring. That's boring. We'll make a size of list, and we'll append that. Okay, then we can also plot the. Oh, did I change that somehow? Oh, it's not size. Oh, size of list. That's n item. So this is memory. Memory size of list. We'll take the size and then the memory size. There we go. We'll see how much memory it's using, right? We can, because you can do more than one plot, on a single graph. Because the printing is actually pretty slow in terms of printing. Okay, so it does get smaller here. The size of all of our timings are screwed up now. So yes, that's maybe we should do a second plot. That's okay. Here, let's comment this one out. Let's see. We're just kind of experimenting and seeing what happens and looking at it using some of these timings to kind of visualize what's happening here. It was kind of part of the fun of the lab. I don't know if you thought it was fun or not. Right, so we're big, we shrink, we get a little bit less big. Why is it not? Size of list. Length of value. So it should have been decreasing. Let me put a breakpoint in here. It should be going down. Excuse me. There we go. So size of list. Yeah, so that's decreasing. That's good. Decreasing, decreasing, decreasing. We got timings, we got values. Did values not fit? Oh, because we're removing. I did a bad thing. I stopped. I was iterating over this. That was bad. Okay, that's why it was cutting off at 50,000. Okay, that was the problem. So we want for range of length of values. Right, because as we're removing things from values, our for n loop is changing and messing up here. That ought to be a little better now. There, so now we can see the size changing. Cool. Okay, so it is shrinking. So when we saw those the tall bars and how long did it take to remove those things, right? As it shrinks, it's actually freeing up some of this memory space. So the list is smart enough to shrink itself. So like the list would expand itself and the size would increase as we went. Every so often, like do that doubling. It's doing like a halving here, essentially, behind the scenes. Right, that was the goal with showing that one. So let's go back, comment that one out, and see if we can get the timings now with it actually working better. Right, so we still see the spikes where it's resizing, looks like. You know, and in terms of timing, it's not too much more, right? This is really quick, essentially, but you see lots of shifts. Like it's very slow until it gets down to a small enough manageable size, the shifting. That's kind of cool for looking at the removes, right? And then we want to look at inserting at an index. So we'd expect it as the length of ours to get longer and longer and longer. Okay, so we'll comment all those ones out. Let me leave those plots up here. What is it? Edit. It's no, convert. Where is it? Code. There we go. Comment. Should be in here. There was a shortcut for it, and I'm not remembering it now. Comment. It's not that. Comment with line comment. There we go. New is there. Okay, so now we're going to try the compute time to insert. Okay, so again, we'll have a timings list. Right, and then we'll have, some lists here to add to. And then we want to, for n in range, I don't know, let's try 100,000 and see how well it works. This one should be still a little slow because we have to do all the shifting here. We'll take our timings and we're going to append the compute time. Given my sum list, and I don't know, we'll just add the n here. Then we're done. We're going to plot.show. So we're going to show the sum list, right? That's not right because we want, what do we have here? Values, right? A list of that. We just do range of 100,000. Because I know that's the size, right? If we add one item, we're size 1. I guess we could do size of list, and items in list. It's in list. And we'll append n plus 1. Or we can do length, right? Why not? Length of some list. Length of list. I like that. Length of list. That'll be our x, and the timings will be the y. We should see a correlation here. Okay. Relatively quick. The spikes there are when we have to resize behind the scenes. Right, as our list runs out of that extra free space, because the list keeps that extra free space here, then it has to go and do the doubling, where it copies them all over. So we see a bunch of the tall bars, but it's faster to shift than it is to do the copying. Let's run it one more time, see what we get. Okay, that one was particularly slow. It's like one slow one kind of throws off your whole graph. It's a little funny. So this is like runtime analysis, how long it takes to run, is never very precise because your computer is always doing other things at one time. It's really hard to get it completely isolated with all the background stuff that has to happen. Okay. That makes sense what we were trying to do for the lab there? Just look and try and explore some of these things. See what we ended up doing. Right, so all of this is all about trying to understand what lists are fast at and what they're slow at. Right, if we have that additional space, it's really quick to add at the end. But if we have to add at the beginning here, it's going to be much slower in comparison. Right, because at the beginning we have to do all of those shiftings. The insert. Yeah, so we're just calling insert, and it's index, and then what's your insert? The value doesn't matter. It could just be a 0. We don't really care. We're just calling insert at a given index. Yep. So we just loop, and we're using that method, and then we'll return the timings. We just add it to our timings list. So I'll put that one out here in GitHub. Yeah, no problem. So this is 2001. There we go. This is lab 2. And just looking at exploring, we'll do similar things with the other data structures as we start building them. Stacks and queues they don't work quite the same for us. Excuse me, we won't do quite as much exploration with them. We're going to use stacks and queues and try and explore what they do. And then our next project will be based on stacks and queues. They're interesting data structures. So unfortunately, I've got to get running here in a minute. My little guy is about done with playing with the bigger siblings. My wife's still not feeling well, I'm sorry. So we'll pick up on Thursday. So the append is we're appending the timing here. So remember, our function just returns the time that it took to do something. So I'm inserting the time that it took to my timings list. And then the function itself is doing the piece to the list that's doing the insertion here. Right, so find me in Discord. Let me know if you have questions about the maze solver. I think I've talked to a couple of you, and it's going relatively well. You're on pretty good track to get that done. Remember, when you're tracking which is the fastest solution, right? It's just like finding any sort of mitten. You just take every value you get, and you see if it's the new lowest. Okay, so you got lots of options there for tracking the shortest path. Yeah, thanks. I'll post it out there, and I'll also be around a Discord. I can chat on my phone without too much trouble while supervising the little guy. So I've got that committed, pushed out to GitHub. You should be all set. All right, sorry to run. You guys take care. Hope you do well. And let me know if you need anything. All right, I'll be around. You guys take care.